All right, let's kick things off with a question that sounds, well, kind of impossible. How do you photograph a single atom? I mean, something so small you'd think it's fundamentally invisible, right? Well, it turns out we can. And the tech that lets us do it has literally changed everything about how we see the world.
So today, we're going to break down exactly how these incredible machines, electron microscopes, pull it off.
And to really get a feel for their power, let's start with a little comparison. This is going to show you just how much of a hidden world they can actually reveal. Okay, so if you take a standard light microscope, the kind you probably used in high school science class, a butterfly wing looks like this. You can see it's made of these tiny overlapping scales. Pretty cool, but this is pretty much the limit. This is as close as light can get us. But now, switch over to an electron microscope. Whoa, suddenly it looks like an alien landscape, doesn't it? Each individual scale has this incredible, almost artificial-looking texture. It's a whole world hiding inside another world, and we were totally blind to it before this technology existed. Let's put some numbers on this, because the difference is just staggering. A light microscope, it maxes out at about 2,000 times magnification. If you try to push it any further, everything just turns into a blurry mess. But an electron microscope, it can hit a useful magnification of 2 million times. That's not just a step up, that's 1,000 times more powerful. So what's the deal? I mean, why can't we just, build better glass lenses and keep zooming in with light? Well, the answer isn't about engineering. It's about the fundamental physics of light itself.
Yeah, it really feels like we should just be able to keep zooming in, right? But there's a hard physical wall we hit, a barrier that light just can't get past.
And that wall is something called wavelength. Okay, here's a super simple way to think about it. Imagine you're trying to measure a really tiny screw. You can't use a ruler that only has markings for every inch, right? Your ruler's markings have to be smaller than the thing you're trying to measure. Well, in microscopy, the wavelength is your ruler's markings. And if the wavelength of light is bigger than the object you're trying to see, it's like trying to feel the details of a grain of sand while you're wearing a huge, thick oven mitt. The light wave just kind of washes over it without resolving any detail. And this is where the genius of the electron microscope comes in. Look at this. The wavelength of visible light is about 540 nanometers, but an electron, once you speed it up, has a wavelength of just 2.5 times picometers. I mean, a picometer is a trillionth of a meter. That's over 200,000 times smaller. We didn't just get a better ruler, we basically invented an entirely new system of measurement on a microscopic scale. Okay, so now that we've got our new light source, the super powerful beam of electrons, it turns out there are a couple of main ways to use it, and it all depends on what you're trying to see. The two big players are the SEM and the TEM. Think of the scanning electron microscope, the SEM, as a surface mapper. It scans the outside of an object to give you those incredible 3D-looking textures like we saw in the butterfly wing. Then you've got the transmission electron microscope, the TEM. This one is more like a high-powered X-ray. It fires electrons through a super thin slice of a specimen to see what's going on inside. And as you can see, the TEM is the real heavyweight champion here. Its resolution can get down to 50 picometers, and yeah, that is absolutely small enough to see individual atoms. So, since the TEM is the one that can see atoms, let's focus on that. For the rest of this breakdown, we're going to follow an electron on its wild journey through one of these amazing machines. The whole process basically breaks down into 6 key steps. First, you've got to generate the electrons. Then, you accelerate them to an absolutely insane speed. We're talking like 70% of the speed of light. After that, you have to focus that beam to a tiny point. Then comes the magic moment. You shoot that beam through your sample. As the electrons pass through, they get altered, picking up an imprint of what's inside. And finally, you magnify that electron pattern and capture it as a picture we can actually look at. So you might be wondering, how in the world do you focus a beam of electrons? I mean, you can't use a glass lens, right? This is where the engineering gets super clever. They use something called a magnetic lens. It's basically a set of powerful, carefully shaped magnetic fields. As the electrons zip through, these fields bend their paths, steering them all toward a single focal point. It works just like a glass lens focuses light, but for electrons. It's an absolutely brilliant solution. And in that whole system of lenses, there's one that's considered the absolute heart of the microscope, the objective lens. It's the very first lens that interacts with the electrons right after they've passed through the sample.
And here's why it's so critical. Any tiny little flaw or imperfection in this lens gets magnified by all the other lenses down the line. So the quality of this one single component basically determines the final resolution of the entire, multi-million-dollar machine.
Oh, and get this. Here's a crucial detail that's just wild. The entire column where all this magic happens, it has to be a near perfect vacuum. We're talking outer space conditions. Why? Well, if even one of those super fast electrons bumps into a single stray air molecule, it'll get knocked off course and completely wreck the image. So yeah, the whole trip happens in a total vacuum. All right, so we've generated, accelerated, focused, and transmitted our beam. Now for the grand finale, turning that invisible stream of electrons into a picture we can actually see. And the way they do this is pretty smart. It's a two-part system. First, the electron beam hits a special phosphorescent screen. Think of it like an old-school TV screen that glows wherever the electrons hit. This gives the scientist a live, kind of low-res view so they can get everything lined up perfectly and find the exact spot they want to image. Then, once it's all dialed in, that screen slides out of the way and a super high-resolution digital camera moves into its place to capture the final, beautiful, science-grade image. So why does any of this matter? I mean, why go through all this trouble? Well, because this isn't just about getting cool, futuristic pictures. This technology is, and I'm not exaggerating, at the very heart of the modern world. It's how we design the tiny transistors inside the phone you're probably holding. It's how we can see the structure of a virus to create life-saving medicines. It's how we can engineer brand new materials, literally atom by atom. This is the tool that lets us finally see, and more importantly, build at the very foundation of reality. And that really brings us to the most exciting question of all, doesn't it? Think about it. For basically all of human history, we've been building things while blind to their fundamental building blocks. Now, for the first time ever, we can actually see them. The era of designing things atom by atom isn't science fiction anymore. It's here. So the final question isn't just what can we build now, it's what will we build next?